Take a look back at your notes. Send yourself back to the last time we were together. What were we doing? What were we trying to figure out?
Like the something to do with how far the moon moves or the speed of around the Earth or something.
Like figuring the force that it had on the Earth moving around the sun and the moon.
Yeah, so we're talking about the force, right? That we're trying to figure out how big that force is. And we know that that's a force of gravity, right? That's keeping it in a circle. So we know that gravity is equal to, or the force of gravity is equal to mg, right? So then the next part of the question, I think this is kind of, Trayton, where you were going, was trying to figure out how far the Earth was going to fall. So let me, before we jump into that, let me clarify this a little bit. You guys have heard of Isaac Newton? We've talked about Isaac Newton. You know kind of how I feel about him? Not my favorite person. But he did do some clever things. One thing he did was to draw a picture in one of his famous books that gives some really good perspective to things that we understand. So he drew a picture of the Earth with a really tall mountain on it. Okay? And he asked people to think about throwing something off the mountain. Like, I don't know, maybe a frog. Okay? So let's throw a frog. If we just throw a frog off a mountain and we zoom in, so really like here's the jagged peak, and I'm standing right here with the frog, and the frog is right here, and I throw him. I'm going to throw him horizontally. Is that okay with everybody?
Uh-huh.
I'm going to throw him horizontally. What's he going to do? He's going to fall. Is he going to fall straight down? No, he's going to do some projectile motion, right? He's going to fall in a parabola. Life is good. He's going to land like that. Does that make sense? So if we draw this in this big picture, let's say that I get a little bit stronger arm. Okay, I worked out a little bit. I've got really, really good throwing ability. So instead of just throwing it so that it hits the mountain, I can now throw that frog so that he falls and he hits the Earth. Does that make sense?
Uh-huh.
Is that okay? And then, see, that's kind of the limit of how hard I can throw the frog. So now I get a frog launcher, because I had one before, right, with a little spring-loaded thing. And I push it back. What's that?
I thought you sent it back.
I did this example first. I did this experiment first. Then I did send it back. I'm one of those people that returns used things. Shh, don't tell. It's a bad habit of mine, right? Send it back. I'm going to launch him horizontally, but now he's got more velocity. What does that mean about his trajectory? Where's it going to go? He's going to go farther, right? His range is going to be farther. So you may want to draw this picture too. It's kind of fun because now he goes like this. Oh, and he goes farther and he hits the ground. Then I buy the super industrial size frog launcher. Okay, it was on sale on Black Friday. We got it. It was from the frog launcher store. I don't know if you guys have one of those near you. I was visiting family out of town and the frog launcher store was there and I bought one. Super jumbo size so I can launch him even faster. What's going to happen?
He's gonna go like curve around the Earth. And
He's going to
like,
fall, and he's going to keep falling, and he's going to keep falling, but what's the problem? Where's the Earth?
back there.
Down.
It's down, so he's going to keep falling, right? He's going to keep falling, and he's going to keep falling, and let me draw the picture instead of just drawing it with my finger. He's going to keep falling and falling and falling and falling and falling. Does he ever hit the ground?
Well, eventually.
Does he? He's just going to keep falling and falling and falling and falling and falling and falling, right? You with me here? That's not perfect, but you get the idea. And did you know that with the super industrial launcher, they also sell a helmet? Because my issue is that I'm standing up here on that top of that mountain, and I project the frog in this direction, and then I'm like looking with my binoculars, right? Like, where did the frog go? And all of a sudden, boom. Right? In the back of my head, here comes the frog, because he's fallen all the way around the Earth. He fell the entire way around the Earth. Does that make sense? That's a little weird. Would you agree?
Makes sense. It would make sense.
So it fell but never hit the
Right, because the ground kept moving out from underneath it. That's what an orbit is. That's what an orbit is. An orbit, if you look at any point, it's got some velocity, right? In the x direction, in that what we call the horizontal direction, and it's going to keep falling in the vertical direction. In this case, though, that ground just keeps moving, and that is circular motion. Does that make sense? Mm-hmm. So projectile motion, that stuff that we spent all that time on, is really just a very specific case of orbital motion, okay? So to launch the frog into orbit, I just need to have a high initial velocity perpendicular to the surface. Fletcher, it looked like you had a question.
Yeah, so wouldn't it eventually like slow down?
Right, so we're assuming a lot of nice things, right? We're assuming that there's no air resistance. We're also assuming, so there's no atmosphere, right? So that's kind of a problem. But we're also assuming that this mountain is taller than anything else on the Earth, right? Okay, so there's a lot of assumptions. This is more of a thinking question than an actual let's go try it question, right? I'm not actually going to go do this. But that's how one could get something in orbit. Is that like the best way to get something in orbit though?
No.
Like realistically?
No.
Certainly not. I mean, there's the whole like problem of really tall mountains. There's also the problem of the atmosphere. And there's also the problem that you don't want things orbiting just as high as the mountain is, right? Like that's a problem. So they usually have to launch them out, right? They give them some initial velocity in that direction to get them moving, and then they allow them to fall, okay? So the satellites that power all of the lovely electronic devices that we use, all of the news services that we rely on, all of those satellites are falling in orbit around the Earth at a certain distance out. Yeah?
Is there a specific, like, amount or, like, point where, like, if it was, like, lower than that velocity, like, when it was
There is, yes. And we could, excuse me, we could calculate it. I just don't care enough to do it right now. Is that fair?
Yeah.
I mean, we certainly could. It would take 20 minutes to figure. We have to look up some information and whatever. We could do it. I just want to do other things. Is that fair? Yeah. Go.
Okay, so I don't remember his name, but you know the guy that, like, jumped from the side of, or space or whatever, you know? He jumped from, like,
Fearless Space?
Yeah.
Uh-huh.
For that, would he, like, if something went wrong, would it be possible if he, like, went into orbit?
I don't think he was high enough up.
He wasn't? Okay.
I don't think so. I don't know the details. I remember hearing about it. I don't remember, like, you know, all the bits and pieces. I just don't think well, there were two problems. I don't think he was high enough up. And as a result, I don't think, I mean, the whole air resistance issue comes into play.
Hey, look, there's a house.
Right.
There's a house again. And
Right.
again.
But
And again.
if it was up high enough outside of the atmosphere, then sure. Although, you know, there's some other issues with that, but yes.
Like smack
Yes.
into the International
Go.
Space Station.
But on the other hand, I'm pretty sure he jumped it pretty much completely vertically with very little horizontal force.
Right.
Floor down, down.
Yeah.
Do you know
An initial horizontal velocity, otherwise you're going to fall. Speaking of, because that's actually leading us to the next thing, if that's okay. Can I move on? Is that okay?
Yeah.
So, the next question that I asked you how far the frog was going to fall in a second, like if I just let him go, and we figured that out, right? We did that last Friday before we left. And we figured that he was going to fall almost 5 meters downwards in 1 second. Is that okay with everybody? And then I asked you, and this was the weird question, like, what are you talking about, Carmeling? This is weird. How far would the moon fall in 1 day? So I think a lot of you are like, okay, I'll plug numbers in because I trust you, but I don't know why you're asking me this. So here's the thing, is that when we talk about the moon falling, it's got some velocity going this way, so it's not actually going to fall that far, but it will fall in the radial direction some distance, okay? we calculated that it would fall 3.6 times 10 to the 10th meters in the direction that's radial, right? So that makes sense, like downwards while it's moving. But so it would be like projectile motion, but it's going to fall that far. Is this a big number or a little number?
Big.
It's a big number. Go, Gemma.
Would that be like the circumference of its orbit, or would it literally be falling towards the
It would be literally falling towards the Earth
Earth? Does
this far.
it go back, or is it still falling? Like,
Do we
are we
have to
eventually
worry
going to be
about-
crushed by the moon?
Okay. I love that question. Are we eventually going to get crushed by the moon? Here's the thing. Sometimes I lead you in places that are a little bit funny. Let me tell you why this may be a little bit concerning to Gemma and maybe to the rest of you. Here's the thing. The distance between the moon and the Earth is only 3.85 times 10 to the 8th meters.
It's so big.
This is a big number also, would you agree?
Yeah, but it's a
But it's a lot smaller than this one.
Yeah.
And so what this tells us is that this distance can't be right. This would mean that the moon would fall, right, a lot further than us every day. And does that happen?
No.
No, it doesn't happen. Okay, so I just led you into a big, wall. Darn it. There was an assumption that we made. There was an assumption that we made when we made this calculation. What was the assumption that we made? Anybody know or want to? Yeah.
That it was falling over a flat surface.
Kind of. I mean, the laws of physics shouldn't change. Like, this equation should still work because when we found this equation, it wasn't like
Oh, it had no velocity.
in the horizontal direction, but that would be okay. That would still mean if it was going in a projectile trajectory, that it's still going to fall toward the Earth this far. Do you see what I'm saying?
Yeah.
There's a problem here. Yes?
Is it because technically it's still falling when it's in orbit? Does that mean how far it's gone?
So that's kind of like what Becca just said. It kind of means that, but it also means, so instead of going in this nice circle, it means that it would go like this, right? And it would go like way over here in 24 hours. And that's not, you see what I'm saying? Actually further than that, like way further than that.
Is it like the F net is? Never mind.
You're really close.
'Cause,
Keep
like,
talking.
Well, the forces are like going different ways, so never mind.
You're close. You're almost there. Rachel wants to say something too. She's like, I wanted to talk.
The acceleration would be different.
Oh. We made this assumption, right? We made the assumption, we know that gravity's the thing that's pulling it in, but we assumed that the acceleration due to gravity at the place of the moon is still what? 9.81. Is that a constant?
No.
It's not. We talk about it as a constant because, well, we're hanging out at the surface of the Earth all the time, right? But is the moon hanging out at the surface of the Earth? No. The moon is not hanging out at the surface of the Earth. And the big thing that Isaac Newton did, right? Like, I'm not his biggest fan. But I'll give him credit for this. If you walk up a street and ask somebody what Isaac Newton did, I would guess 60% of all people would tell you that Isaac Newton invented gravity.
Yeah.
Right? Now, there's a problem with that verb. What does it mean to invent something?
Me, like,
Whoa, it's like go, somebody speak.
alright. It means like it wasn't there before. It didn't exist. So,
Right.
People were just floating around.
Woo! Stupid Newton, like totally like bringing us all down, right? Like that's not very did, and I will again, like I said, give him credit for this. He was the first one to suggest the idea that gravity is not constant, that the acceleration due to gravity changes depending on where you're at. So when you take AP Physics with me, we'll go through and do this whole derivation, but I'm not going to go through that with you right now because I want to do some more stuff with it, okay? But this is what Isaac Newton suggested. He said, yeah, Galileo, you say Fg is equal to mg. I think that's only true at the surface of the Earth. Okay? When you go further out, we need to talk about it in very different terms. Gravity is a force between how many objects? Two objects. Gravity exists, this is really important, between any two massive objects. What does massive mean?
Having mass?
That it has mass.
That it has mass. If you say massive to somebody on the street, they're going to say that it must be really what? Humongous. But, my friends, this is not a statement about any, like, you don't have to, like, take this as, like, a personal, affront. You are all massive. Okay? You are massive. I'm not saying you need to lose weight. I'm just saying you have mass, right? Any two massive objects have a gravitational force between them. You have a gravitational force acting on the Earth, but you also have a gravitational force attracting you to the frog. The frog has mass. You have mass. There's a force between you and the frog. Okay? It's an attractive force. It has a value that we can calculate. We can find it using this formula. We need to break this down because it's a little funny. Let's look at the things we understand and know for sure. M1 and M2 are probably the masses of the massive objects, right? Okay, so those are pretty easy to deal with. Any idea what R might be?
Like radial distance between center of mass 1 and center of mass 2.
Yes. So R is the distance between the centers of the objects. Okay? The distance between the centers of the objects. And then we have this G. Now, you have to be very, very careful, my friends, because sometimes, I don't know about you, like sometimes when I'm writing things, I'll, switch capital letters and small letters, just kind of willy-nilly, whatever. Whatever. Don't do this here. This is a little g, right? What does little g represent? Gravity doesn't mean anything. What is
Acceleration due to gravity.
on the surface of the Earth? This is the acceleration due to gravity on the surface of the Earth. It has a value of what? Negative 9.81. Units are? Okay. We understand that, yes?
Yes.
Fabulous. This G is not the acceleration due to gravity. This little g is not actually constant. If you go up to the top of a mountain, it's a little different. If you go down to Death Valley, it's a little different, okay? It would be like a little different. Like we don't have, do you remember like at the very, very beginning of the year, we were talking about having better or worse meter sticks and being able to measure better, right? You would have to have such a good measuring tool, right? Like ridiculously good to actually perceive it. But yes, it is a little different. Yeah. This G here is known as the universal. It's like she took the words right out of my mouth. universal gravitational constant. And this one is, in fact, constant. We can use this rule, this law, anywhere in the universe. This works when we're talking about us on the Earth, but it also works for the moon and the Earth and the sun, or the sun and our galaxy. Or a really, 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 really far away pair of binary stars. Anything works with this statement, which means that this constant is, in fact, constant. Like, it doesn't change where you go, okay? This has a value of 6.67 times 10 to the negative 11th. And the units are crazy town. Newton, meter squared per kilogram squared. Now, so I want you to write that down so that you know what it is.
Oh, got it.
Okay?
Can we just like create a board for that?
Nope. Newton meter squared per kilogram squared. We just use it. Now,
Why can't we just do these fishes?
question, Gemma?
Like, how did they figure that out?
That's a really good question. Let me say one other thing and then I can tell you how they figured it out. Is that fair?
Okay.
Okay. So I just want to make sure that this unit, like, how do they figure the unit or the number?
The number.
Okay. So let me figure out the units first because the units are easy. What is this going to be measured in? What units? Newtons. So we got to have newtons in this thing, so we have newtons that are coming out, right?
Yeah.
What are the units of R?
Meters squared.
Meters, then it's squared. So we need meters squared to go away. So we have meters squared in the denominator. This thing needs to have meters squared in the numerator. Does that make sense?
Mm-hmm.
So that they'll cancel. And then the masses are measured in kilograms. There are two of them, so it's going to be kilogram times kilogram squared. So that's got to go in the denominator so those can cancel. Does that make sense?
Yes.
So that's how the units work. How in the world did they figure out that number? It's really a good question. So the secret that I feel like I need to tell you, because, you know, I'm not Newton's #1 fan, Newton didn't actually figure this out. Oh, this is what Newton figured out. He figured out that the force of gravity is proportional to, that little thing means proportional to, m1 times m2 divided by r squared. He figured that out. I mean, that's pretty good. But you know that if something's proportional to something else, there's got to be some sort of constant in there?
Yeah.
The constant was figured out by this guy named Henry Cavendish over 100 years after Newton published this. 100 years, that's like a long time, right? That's a long time where they were just living with this. So this guy named Cavendish figured it out. Yeah, go, did you have a question? Or you just itch? Okay, I just want to make sure I wasn't missing something. So the way that they figured it out was pretty clever and kind of surprising. Took them 100 years to figure it out. That's kind of intense. Because the force of gravity on the Earth is so strong compared to any other force of gravity that we know. Yeah. Yeah, of course. Yeah. So this is what he did. He took a little piece of, I'm simplifying this a little bit, but he took a little piece of fishing line, and he took a dowel. Do you guys know what a dowel rod is? Like a piece of wood, and hung it from the string. And then he put masses, he massed them, so he knew exactly how much mass there was on each of these, on each end, so that it would balance. So far, so good? So, oh yay, we have this pretty little balancing thing. And then he also took a little mirror, and he hung the mirror on the string. Life is good so far. I love that face. He's like, why? What are you thinking? What are you doing? Right? Exactly. So here's the game. Here's the deal. We have to be able to know everything else in here so that we can figure out the constant. Does that make sense? So we need to know the masses, we need to know the distance, and we also need to know the force. Now it's interesting that you asked me this question, John. I'm really glad that you you did. Because I said that we were supposed to talk about torque today, right? That's what the calendar says. We're going to talk about torque. Shh, don't tell. We're going to talk about torque right now because if I apply a force to this object, is it going to accelerate?
Yeah.
Yeah. Is it going to just go in a straight line?
No, possibly not.
Possibly. I mean, I don't know. It's hooked to a string and it's hanging. Is it going to go in a straight line?
Depends on which direction.
I'm pushing it like this. Where's it going to go?
Yeah, like it would just swung that way. Or are we going around?
I feel like you're gonna spin.
Is it sweet?
I don't have. I'm trying to like look for something that I can show you.
Straight, like just.
So it's hanging like this, right? So it's hanging like this. Let's imagine this is my string. My finger is my string. Where's the 50 there? So it's kind of even like this. I'm going to push on it like this. Is it going to go in a straight line?
No.
No. It's going to turn, right? It's going to
Circular motion.
motion a little bit, right? Okay. So I'm applying a force, and that force is actually a torque. We'll talk about what that means in a minute. Is going to make this little mirror rotate. Are you with me there? And the rotation of the mirror is directly proportional to the rotation that's happening here. Because it's all rotating together. That's why we need a mirror. Because then we're going to take a fancy little light source. We're going to shine that light source in, and it's going to hit the mirror. And what's it going to do once it hits the mirror? Reflect. It's going to bounce off to somewhere else right over here, right? And we're going to be a what?
It's gonna move as you
Yeah. So as that mirror turns, then that reflected light is going to move from one spot that it was being reflected at to another spot. Is that okay?
Yeah.
Use some fancy pants geometry. We're not going to make it spin all the way around. We're just going to make it's going to move ever so slightly. And the ever so slight movement of this can tell you the force that's acting here. Is that okay? So we need one more mass, though. So they took another mass, another thing that they knew the mass of. And the pictures that I always see, like, make it look like a little lollipop, like it's sticking like that. And they bring this mass really close to this mass, a certain distance away. So we know this mass, and the distance. And I know how much of a force that's feeling because I can measure that movement. You with me there? It was hard to do this, especially back in the day. This is like way a long time ago, to figure out what that G was.
Okay.
Right? Kind of weird, but it works.
So the lollipop mass actually pulled on what you have shown in
The
red.
pink mass,
The
yes.
pink mass there.
Mm-hmm.
How did they?
Not a
And
lot.
I was gonna say, because wouldn't it be like too small to?
Well, that's why it took 100 years to do it, right? It took some pretty careful experimentation. Because it's not going to pull on it a lot, but just a little tiny bit, and that little tiny bit's going to cause that light to move ever so slightly, but we can measure that, we can measure angles, and then we can figure all the rest of it out. We're going to go here and then there. Go.
How would the movement of the mirror calculate?
So the movement of the mirror tells you the rotation of this, and using torque, which we're going to talk about next time, given that rotation, you can figure out the force. Can I leave it there for now? And remind me next time when we talk about torque, and I'll tell you how it works exactly. If it doesn't become perfectly clear, write it down on your notes so we don't forget. Is that what you're going to ask too, Brittany? Or Bridget?
Yeah.
Okay. Are we okay? Okay. So, that was a little aside, but it was a good one. I want to go back to this thing because it's weird. For the last, how many months have we been together?
4.
4 months? It's been 4 months? Wow. We go back a long way. I've told you that FG is equal to this thing. Today I'm walking in and telling you it's this. Have I been lying to you the whole time?
No.
Not entirely.
Both is true.
You just haven't told us everything.
Told us the whole story.
I hadn't told you the whole story yet. I want you to do me a favor real quick. You need to get a calculator out to do this. I'm going to tell you that the radius of the Earth is 6.37 times 10 to the 6th meters. I'm going to tell you that the mass of the Earth is 5.98 times 10 to the 24th kilograms. And then I'm going to point out that if I put a big yellow box around this, that big yellow box, given these numbers, might tell you something interesting. I want you to calculate the value of that yellow box at the surface of the Earth. So I'm the other object, right? The force of gravity, the force of the Earth on me would be my mass times the acceleration of gravity, or my mass times this stuff. Plug those plug those numbers into the yellow box. Don't forget to square the radius.
Oh, I got 9.83.
Yeah.
I got 9.83. Okay, I got 9.
So when you plug in those numbers,
It's 9.8.
that's pretty darn close. And this is the average radius of the Earth, right?
Okay.
So, it's a little plus or minus. That's pretty darn close to our 9.81.
How did they figure the radius of the Earth?
That is a really good question and a discussion for another time, but it's not that hard. But I don't have time to do it right now. Fair enough? It's geometry.
Got it.
Geometry in the sun. All right. So, are you okay with this? Anybody not quite sure still? Can I help anybody? I have another task for you to do if you're ready. I would like, so here's the cool thing about this. This equation, like I said, works anywhere in the universe. This allows us to figure out a whole lot of stuff about the universe just by looking. The lovely thing about astrophysics is that there's so much out there. The hard thing about astrophysics, as opposed to any other kind of physics, any other kind of science really, is that you can't do experiments, right? All you can do is observe. So we have to be able to observe and be able to tell things like masses and radii and speeds. And this thing helps us. Okay? So here's the next question that I want you to solve. The next task that I have for you. I would like for you, and I'm going to have you work in your groups, and this will take a little thinking, but I think you can do it. I would like you to determine the orbital speed of the Earth as it orbits around the sun. You may need to know some other information, so let me tell you things that might be helpful. The mass of the sun is 1.99 times 10 to the 30th. The distance from the sun to the Earth, so I'm going to write the radius from the sun to the Earth, is 1.5 times 10 to the 11th meters. From that information, you should be able to determine for me the orbital speed or the velocity of the Earth as it goes around the sun. You need to write some stuff down. You need to talk to your teammates. I think you can do it, though. I'm going to give you a couple minutes to take a look.
Acceleration.
I got it. 9,700.
Oh, no, I didn't swear.
Okay, I was going to say, I just sort of had a small face. I was freaking out time to start. Like, okay, it has this 8.84. square, there is no velocity in this equation.
Can I pause you for just a moment to just kind of to kind of regroup and make sure we're all okay? I don't want to talk over you, so if you could be quiet, I'd really appreciate it. Do you need to go get something? That's fine. So, just in case it didn't make sense when I said it earlier, the net force acting on the Earth is a gravitational force, right? Does everybody agree with that?
Yes.
That's the thing that's keeping it in circular motion. Do they not work?
Yeah.
Oh, why don't you put it not back in the box? Otherwise, it's just going to be a repeated thing. Just set it on the side and I'll get it later. There you go. The force of gravity we know is this GMM over r squared business. But that's equal to the mass times the centripetal acceleration. Is that okay with everybody? What is this mass? What is that mass? Earth. Who said Earth? Why do you say Earth, Tanner?
Well, because we're calculating the force of gravity.
Right. Yeah, this is the force of the sun on the Earth, right? The Earth is experiencing centripetal acceleration. Remember, every time that we write F net equals ma, the mass here is the mass that's feeling the acceleration, right? What mass is feeling acceleration in this problem? The Earth is feeling an acceleration in this problem. So that's got to be the mass of the Earth. Now, that's fine. What are the M1 and M2 over here?
The two mass, like the mass of the sun and the mass of the earth.
The mass of the sun and the mass of the Earth. Do you care which one's which?
Not really.
I don't care. What do we want to do, Jake? Which one do we do which?
Mass of the sun.
Which one's the mass of the sun?
The second.
The second one. All right. The mass of the sun, so that means this is the mass of the Earth. I want to know the velocity, right? The orbital speed. So now I can do some algebra, right? To get the v by itself. Does anything cancel out? Take a look.
Cancel out one of the radii.
One of the radii will cancel, absolutely. Is that okay? If that didn't make sense, you can multiply by r on both sides to get v closer to by itself, and you're gonna have r on top and r squared on the bottom. So one of those r's is gonna cancel.
And then the mass of the Earth cancels then too.
Yep, there's a mass of the Earth on the top on both sides. So now I've got g ms over r is equal to v squared. Are we okay? Yep. But we want to know v, not v squared, so what do I need to do? Square root it. And now you can tell me the velocity or the orbital speed of the Earth in orbit around the sun. And it's not going very slow, is it?
No.
Check with your table and make sure they agree, and then we'll corroborate. Check with your table, make sure that everybody at your table agrees on that velocity.
It's just gonna ask so that I don't mislead my group. And
Oh, I can look home and say, yeah.
Where do you get the mass of the Earth times velocity squared over r?
This thing right here. So that let me back up one step. That's really like ma. Is that okay?
Oh.
But it's the centripetal acceleration. That's where the v squared over r comes from. Does that make sense?
Yeah.
Okay, good question.
Wait, centripetal acceleration is v squared?
Yep.
yeah, I
Yep.
did it kind of differently, so I'm not sure if I did it correctly, so that's why I'm asking.
So S is just sun. S is sun.
The mass of the sun. Yep.
Okay, I did something before you talked and I got that. I'm not sure what I did, so
So what's your question then?
is it correct?
I'm not gonna tell you that. I want you to figure it out.
Nothing.
Well, but you do it, close down my head, blah blah.
How do you know that it's equal to the like mass theorem? I'm just confused.
Which one? What?
How did you get the g m1 m2 over r squared equal to
Okay, so does this statement make sense? F net is equal to FG? Okay, so that's all we really need to know.
Before she talks.
But F net is MA, right? And FG is the big nasty thing here. And A is the centripetal. So this statement here comes from right here. Is that better? Reagan, how you guys doing back there?
It's constant.
You guys have an answer? Y'all agree? Sweet. What's up? That's a different answer every time.
I messed up in my time machine.
Oh, that's what I got. I gave up.
I just got syntax error on my time, so.
I thought I had.
Is that the right answer?
Yes, sneeze is the right answer.
No, no, syntax.
Oh, yes, that's true. As Nick would say, Nick's awesome.
Wasn't the guy who like found everyone here? He found was about 9,000.
Yeah, what's up? Here? Yeah. Is this statement okay right here? F net is just MA, right? Because it's always MA. But A is a specific kind of A. It's what kind of what kind of acceleration? No, not gravitational. It's going in a circle. Centripetal. And centripetal acceleration is V squared over R. Yeah. Well, I need the expression for acceleration because that's how it fits in here. Is that better? Okay. All right. Are you guys all happy back there?
Yeah.
We think?
Is
It couldn't be operator error, could it? What kind of crazy large answer did you guys get? Esmar, did you get an answer?
Well, if you divide it by, say,
2.97 times 10 to the, what'd you say?
10 to the 15.
Wrong answer. You're close. I think, okay, ladies and gentlemen. I need everybody's attention up here because this is important. Especially when you're dealing with like things that are on astronomical scales. We have all these numbers that are humongo, right? Or tiny. We have to be really, really careful with parentheses. Because if you're not careful with parentheses, you're going to be off by factors of 10. Or lots of factors of 10. So I agree with this part so far. I think she's going to explode if I don't ask her. So you need to tell me if you agree with her after I prevent her from the explosion from happening. Yes?
10 to the 4th.
She says 4th. Do you agree with her?
Yes.
Yes?
Yes.
Yes?
Yes.
Yes? Fletcher, do you agree with her? Yes. What are the units? Now, so my guess is, Mara, that we didn't put things in parentheses. Right. Okay, so, okay. Ladies and gentlemen, so I'm not going to make you go back through it, but I just want to say, in the future, really be careful. Put parentheses around every big number so that it does like 1.5 times 10 to the 11th, and that's the thing that's raised to the 11th power. Does that make sense? Is that what you got?
Yes.
Two? All right. Now,
Syntax error.
Syntax error. It always does syntax
okay,
No, I we all.
guys. My guess is that there's syntax error things going on that it has to do with dividing or square rooting a negative. I can come take a look at it in a minute. What I want to talk about really quick first is I don't have any idea if this makes any sense. Like that seems like a big number, right? Like the Earth is hurtling through space. That's fast. That's 3 times 10 to the 4th. So that's like 3, 1, 2, 3, zoop, 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 meters every second. That's 30,000 of this every second. That's a humongo number, right? That's kind of frightening to me. Like I need to hold on, right? Any way that I could figure out if that actually makes any sense? I just have to trust Believe. Psh, who has time for that? What?
Well, if you know the circumference of Earth's orbit,
Okay.
multiply that number times whatever 360 times 300.
Okay. Can I take that and run?
Yeah.
Okay. So we need something with the circumference because velocity is really just distance. Go away, please. Thank you. Velocity is distance over time. Do you agree?
Yes.
How far are we going? Going around a whole circle. How do you find the circumference of a circle?
2 pi r.
2 pi r. And we need to know how long it takes to go all the way around, right?
Yeah.
How long does it take? How long?
Here.
365 1/4 days, something like that. That's called the period of rotation. The period going around. That was loud. I want you to write now, to solve this for t, figure out what t is and see if it makes sense to you. You may need to do some conversion. Okay? The period.
Yeah,
Right. But pi time. I like that. I like the sound of that, though.
And that's
Oh yeah, 64 and 64.
Okay. So, in the interest of time, and in the interest of making progress, and not just sitting here doing math at our calculators, I am going to. What are you having? Are you getting mad at your calculator? Are you laughing at Jake, who's getting mad at his calculator? Are you okay, Jake?
no.
I'll hold you in a second. All right. In the interest of not wasting a bunch of pi time or whatever it is that we're measuring, I want to make really clear that hopefully we finally got this, that velocity. Does the process here make sense to you? Okay. So 2 pi r over v gives you something like 3 times 10 to the 7th seconds, which it seems like a ridiculous number until you remember, oh wait, it is in seconds. And if you do some fancy conversion, it's not even really that fancy, you can find that something like 366 days, which is about what we want. There was some rounding that happened there, right? So is that a reasonable answer for the velocity?
Yeah.
So we're hurtling through space, friends. Okay. Now the secret of this all is that not only are we hurtling through space going around the sun, but the sun is also hurtling through space going around the center of our galaxy, right? There's a lot of hurtling that's happening. Okay. What I want to do right now is I know that there are lots of questions. I know that I'm opening up lots of little questions, and I love this. I will tell you that there are lots of opportunities to discuss this, but I don't want to answer questions right now because I want to share something else with you that will probably just lead to more questions, and that's fabulous. Okay? How many of you have heard of dark matter? Has anybody heard of dark matter?
I don't know why, but you said
Okay.
dark, I thought you said dark matter.
Okay, you can put your hands down. So, for those of you that have heard of it, if I ask you what it is and you raise your hand with authority, I'm going to laugh at you. Because even the smartest people who have studied dark matter forever in their life, like they've made their entire career of it, don't actually know what it is. It's a weird, messed up thing that makes no sense. But we know it exists because of this. And I want to share with you this a video that's going to kind of lead us to understanding, or to at least maybe appreciating a little bit more, this idea of dark matter and how we found it. Has anybody ever heard of Vera Rubin? Has anybody heard that name?
Blow our mind Tuesday.
Yes, that's my job.
Wait, it's Tuesday, right?
Yes, it is Tuesday. Good job. Good job. Okay.
Still Tuesday.
So, let me have your attention up here, please. So, Vera Rubin is a physicist. I'm hoping this will work. Good. galaxies and studied orbits of galaxies, made measurements, right? Again, you cannot actually do experiments in astrophysics, but you can take a lot of data. And that's what she did. And this is kind of the story of what she did and putting into context what we just did. So they're going to talk a lot about that. I would like you to write down and take some notes over this, because we'll talk about this a little bit more next time, because I just love it so much. We're just going to make it happen. This video comes from a place called the Perimeter Institute. How many of you have ever heard of Blackberries? Like, not the food, but the electronic device, right? The phone. So it was like the precursor to all smartphones, right? The guy that invented it was Canadian, and he made lots of money, as we might expect. And he loves physics. And so with a bunch of that money, he made this thing called the Perimeter Institute. And basically, it's a place that exists, I want to say in Toronto, but I can't remember for sure, where theoretical physicists, those are the ones that just do a lot of thinking, get together and think about physics and teach about physics. And that's where this video comes from. So I would like you to take some notes. I would like you to pay attention carefully, listen, and write down not only facts, but if there are questions that it brings up, write those down too. Does that sound okay? Okay. Here we go.
Frontiers of Science. Join host and physicist Damien Pope of Perimeter's outreach team and leading researchers as they take you on an educational journey of wonder
Blah, blah, blah.
and on DVD.
Blah, blah, blah.
Institute.ca for details.
Blah, blah, blah. Here we go. I don't know why that was so funny, but okay. All right, I would like you to be quiet.
In observatories across the world, physicists young and old are mesmerized by the size and complexity of the universe. Before 1967, physicists thought they had a pretty good idea about what the universe was made of. But that year, physicist Vera Rubin looked at the stars in the outer regions of the Andromeda galaxy and observed something she didn't expect. The billions of stars in Andromeda orbit the center of their galaxy, much like planets orbit the sun. This was no surprise to Rubin. She also knew that planets in our solar system orbited more slowly the farther they were from the sun. So she expected the speeds of stars in Andromeda to decrease in a similar way the farther the stars were from the center of the galaxy. But that's not.
Okay. He talks really fast, and I want to make sure that you understand what he's saying. So, does it make sense, based on that extra distance, that the speed that Jupiter travels around the sun is going to be different than the speed that the Earth travels? Okay. And if you plot that, if you use the equation that we know and love, that we just have like come to embrace today, this is what that graph would look like, right? So here's the Earth, here's Jupiter, it's going less fast. Does that make sense?
Yeah.
So that's what we're talking about. This is a 1 over r squared curve, right?
What she saw. The speeds of the stars remain constant, no matter how far out in the galaxy she looked. What Rubin saw wasn't just slightly different from what she expected, it was dramatically different. The speeds were far higher than anticipated. Why were the stars in Andromeda moving so fast? Was the same thing occurring in other galaxies? Little did Rubin know that her observations would trigger a rethinking of what the entire universe is made of.
The music is really good. The acting is even better. but the content is actually quite good. So.
It's easy to measure the mass of everyday items. A loaf of bread, an apple. But how do you measure the mass of something much larger? Like the sun. To determine the sun's mass, let's use an approach we'll call the orbital method. We can calculate the mass of the sun by measuring the orbital speed and radius of one of the planets, such as Jupiter. Jupiter orbits the sun at 13 kilometers per second. The shape of Jupiter's orbit is essentially circular, with a radius of 780 million kilometers. So how can we use these two numbers to calculate the sun's mass? So let's start with Newton's second law of motion, which says that the net force acting on Jupiter is equal to its mass times its acceleration. The net force is the gravitational force the sun exerts on Jupiter.
You guys doing okay so
The
far?
magnitude of this force is equal to the universal gravitational constant times the mass of Jupiter times the mass of the sun divided by the square of the radius of Jupiter's orbit. Because Jupiter moves around the sun in uniform circular motion, we know that its acceleration is directed toward the sun and is equal to its speed squared divided by the radius. So if we substitute the gravitational force and Jupiter's acceleration into Newton's second law, we get the following formula. If we want to know the mass of the sun, we rearrange the formula. This formula shows there's a relationship between mass and orbital speed.
I'm going to pause that for just a moment. Sometimes when we watch movies like this, you just kind of turn off when this is happening. But I don't want you to have turned off there. Did that all make sense to you?
Yeah.
Do you understand what was going on? Okay, we just did it, right? They solved for mass as opposed to solving for velocity, but it's the same process.
When we substitute in the speed and radius of Jupiter's orbit, we can complete our calculation of the sun's mass.
Hey, that's the mass we got, right?
So what does this number really mean? Only that the sun is 1,000 times the mass of Jupiter and 300,000 times the mass of Earth.
Right, this accuracy is amazing. Right.
Now that we know how to calculate the mass of the sun, let's see if we can calculate the masses of entire galaxies. A galaxy is a vast collection of stars, typically around 100 billion. In many galaxies, gravity makes stars orbit the center of their galaxy, just like Jupiter orbits the sun. Because of this, we can use the orbital method to find the mass of a galaxy within the radius of the orbit of any star we choose. To do this, we need to know the speed of the star and the radius of its orbit. Ever hear of the Doppler effect?
You guys heard of the Doppler
When an
effect?
ambulance rushes past you and the sound you hear changes frequency. As it approaches you, the sound shifts to a higher frequency. As it moves away, it shifts to a lower frequency. When you measure the shift in frequency, you can determine the speed of the ambulance. It's the same with light. If a star is moving towards us, light shifts to higher frequencies, closer to the blue end of the spectrum. If the star is moving away, the light shifts to lower frequencies, closer to the red end. Since galaxies are really far away,
I'm not really good at watching a movie and not talking in the middle of it, so I just want to make sure this makes sense to you. Most of you took 8th grade science last year and you talked about light, right?
Yes.
And you talked about the electromagnetic spectrum and how you got the light spectrum and you got red over here and you got blue over here. Does that sound familiar to you?
Yes.
And they're of different frequencies. So just like sound waves have different frequencies, high and low, that thing that the ambulance does, the same thing does happen with light. Yeah.
What's the Doppler effect?
So the Doppler effect is that new. Have you heard that before ever when like something goes by?
Yeah.
So it gets really, really high pitched. Thank you. It gets really high pitched as it's coming toward you, and it gets really low pitched as it's leaving. Does that make sense?
Yeah.
And I'm not gonna like test you over that. It's just kind of more of a like kind of cool thing. Light does the same thing, and that's the weird part. Is it not only does sound do that it stretches and shrinks, light does the exact same thing. And so it actually, an object changes color when it's going towards you or away from you. Whoa, have you ever noticed that? Like somebody running towards you, their shirt changes color?
Oh yeah, totally.
Not really, because I've done the math and you have to be moving like almost the speed of light for it to actually happen. But these things, actually not the speed of light, you have to be moving much faster than you can run, even you fast people, okay? But these things, so like when you look out at a galaxy, you can see the rotation because of that. Is that okay? Just whetting your appetite, not saying you have to understand all this, not a test over this idea of Doppler effect, is just kind of cool. Okay.
We can't simply measure the speeds of stars by calculating distance over time. So the Doppler effect can be used to indirectly determine their speed. The greater the shift in frequency, the faster the speed. Let's use the Doppler effect to help measure the mass of a nearby galaxy called Triangulum, which, like Andromeda, has stars orbiting at speeds higher than expected. Let's pick a star in the outer regions that's orbiting the center of the galaxy with a radius of 400 million billion kilometers.
Galaxies are not
The
small.
star in the outer regions of Triangulum is orbiting at 123 kilometers per second. Let's substitute those values for speed and radius into
Okay, so just to be really clear, so what they're doing, looking for the mass, you need to know the speed and you need to know the distance, right? So they're finding the speed from this Doppler effect funniness, this blue and red stuff that happens. They measure this directly because you can see that if you're looking at the if the galaxy happens to be facing, so you can see it. And then we know G.
galaxy mass formula. This huge number is equal to the mass of 46 billion suns. 46 billion suns. That's pretty bright. Let's use that brightness to confirm the mass of the galaxy. To start, we'll need a flashlight. If we know the mass of one flashlight, and its brightness, we can figure out the mass of a whole wall of identical flashlights. How? By measuring its total brightness. Let's call it the brightness method. It's another way to measure the mass of objects in outer space. It also helps us understand why Rubin saw the stars in Andromeda moving so much faster than anyone expected. Once you've got the total brightness, compare it to the brightness of the single flashlight. The relationship between the brightness of all the flashlights and just one will tell you how many flashlights there are. Then, multiply the number of flashlights by the mass of one flashlight, and you've got the total mass. We can use the brightness method to calculate the mass of the stars in a distant galaxy within a given radius. But there are a couple of problems. First, some galaxies are farther away than others. For example, Triangulum is farther away than Andromeda. Galaxies that are more distant appear less bright, even though they tend to emit the same amount of light as closer galaxies. But scientists know that, just like the brightness of a flashlight, the brightness of a galaxy decreases in a predictable way based on distance. When a galaxy, or a flashlight, is farther away than another one, it only appears less bright. So scientists can determine the actual brightness of a galaxy if they know how far away it is. The second problem is that, unlike these flashlights, not all stars are identical. Fortunately, there's a relationship between a star's brightness and its mass. that helps account for the different types of stars found in galaxies.
We've got 2 more minutes. Give them to me,
Having
okay?
solved the problem
Stay
of
still.
distance
Keep watching.
and accounted for different types of stars, physicists determined through the brightness method that the mass of triangulum within a radius of 400 million billion kilometers equals 7 billion suns. But the orbital method gave us a mass of 46 billion suns. That's a difference of 39 billion suns worth of mass. Similar mass differences have been observed in over 1,000 galaxies. Something very, very strange is going on. But what? The brightness method assumes that all mass in a galaxy emits light, but the orbital method doesn't assume that. In fact, most of the mass in triangulum measured by this method is unseen mass that emits no light. And because there's a relationship between mass and orbital speed, it's this extra mass that can explain the high speeds in triangulum and in all other galaxies scientists have checked. Such as Andromeda, where via Rubin observed orbital speeds far higher than expected. Most physicists are confident that Andromeda, like triangulum, is dominated by unseen mass, and they think that this additional mass is responsible for the speed she saw. By looking at satellite galaxies and other distant objects, physicists now think that, in most galaxies, this unseen mass extends much farther than the outermost stars. In this image, we represent this mass by the pale blue shape. Because the unseen mass doesn't emit or reflect any light, it's known as dark matter.
So I'm going to pause that right there. I just want to tell you, because this is really weird. All of the mass that we are, that we can see, so you look out the window, you see all that stuff, you look in a telescope, you see all that stuff, all of that, scientists believe, is only on the order of about 10% of all of the matter that actually exists in the universe.
That's freaking.
That's messed up, right?
I feel like a grain of sand in the wind.
What?
Or an atom in the wind.
Have a good day, you guys.